We're going to work through problem 4.26 from Taylor's Classical Mechanics. This is a chapter 4 problem on a time-dependent potential energy. So we're given here that a mass m is in a uniform gravitational field. So the field is uniform. The force is mg, and that's vertically downward. But we have g is a function of time. So gravity is a function of time. So we're going to choose axes with y positive being vertically up and defining our potential energy to be mgy. We want to show that the force is negative gradient of that potential energy. So the force is the negative of the gradient of potential energy. So that's the first part of what we need to do here. So we can start with that. We know that our force is mg, and that's vertically down in the y direction. So that's 0I minus j plus k, or like so. So our force is just negative mg and that the y component. Using this, we want to take the that's what our force is. Now we want to take the negative of that gradient of the potential energy. So it's going to be negative gradient of mgy, which will be negative mg, just the gradient of y. If we take the gradient of y, the x component, this with respect to x, the partial with respect to x is just 0. Partial with respect to y is 1. Partial with respect to z, 0. And we end up with negative mgj, which is equal to our force. So we've gone ahead and shown that the negative of the gradient of potential energy is equal to our force. Now we want to differentiate this energy equation to show that the energy is not conserved. So they're giving us our total energy, our kinetic plus our potential, equals 1/2 mv squared plus u, which we know our u, so we can write this as 1/2 mv squared plus mgy. Now, differentiating this with respect to time, this is going to be alright. Now using our product rules, we're going to use our product rule on this. And on this, we're going to differentiate. We're going to end up with mv dot. So that's actually going to be our acceleration. We'll find out in a minute is g. And dotted with v is if we're leaving them in any sort of vector form here. Now, for this part, we're going to end up with mg dot y plus mg. Alright, we know that this y with a dot on top of it is the derivative of y with respect to time, which is going to be our velocity in the y direction. Just to make that a little more clear, we know that this derivative of velocity with respect to time is our acceleration. So this is acceleration, which in our case is negative g in that j component. So this expression will become negative m This is negative g in the j direction, dotted with our velocity. So let me just write this off to the side. Negative g, j, dotted with our velocity vx, vy, vz. We're just going to have negative g, vy. So pulling that negative over to here, we get g, vy. You can leave that off to the side. And we're going to have plus, we knew that this was our vy as well, plus mg vy plus mg dot y. These two will cancel each other out, and we're going to be left with mg y. This is not equal to 0, so that means our energy is not conserved. So up here we have the negative of the gradient of potential energy is equal to our force vector, though when we go down here, our energy is not conserved.